Okay, so about to get a feel for the problem, often it's a good idea to try some special cases to show that the theorem statement is true for those cases, and you might do several cases, and that gives you some experience, a feel for what the theorem statement or the theorem is trying to say. Now, if you can find a counterexample, just one, then that allows you to kill the theorem statement. You know that it's not true, and you only have to find one example, and that's enough to kill it. Right? Now, of course, if the theorem statement is true, then there's no counterexample possible. Right? Because remember, for a theorem statement to be true, it's true in all cases. It's universally true. Okay? So there's not a single counterexample. There's not a single case where it's not true. Right? Now, are you familiar with the symbol here? There is no, or there is not, or it does not exist. So the there is like this capital E that's mirror image that way, right? And then a bar through it. So that's a very common symbol in pure math, and it just means there is no, or there is not a. Okay, so useful shorthand. Okay, so if your theorem statement is true, then there is no. Oops. Sorry, I don't need that, right? The bar does that. So there is no counterexample possible because it's true. Right? Now, if you go hunting for, and we'll do it here in a minute, a little bit later. If you go hunting for counterexamples and you have a hard time, and you just can't find one, even after a lot of effort, that would make you suspicious that maybe it's true. Now, that doesn't follow logically that that's so, because you may, after quite a bit of effort, finally find a counterexample. But if you put in a fair effort and you can't find one, then that increases the probability that your theorem statement is true. So you get suspicious, right? So then maybe you should change direction and then try starting to actually prove that it's true, that the theorem statement is true, right? By finding a proof. So if you're finding it difficult to find a counterexample, that might give you some clues on why the theorem statement is true, right? So you're going the other way. So then you try to prove the statement. All right. Well, let's now actually start thinking about an actual problem. We'll start applying some of these somewhat vague hints, suggestions on how to go about a mathematical proof. Because as you get into this course, there will be many proofs, and quite pure math-like, with the same, as I was saying in earlier sessions, with the same format as in a pure mathematics text. In other words, like lemma, theorem statement, proof, corollary, that kind of structure. The text, Sipser's text, is full of that. And why? Well, because theory of computation is very mathematical by its nature. Right? Some of it is quite fascinating. Like the theory of what you can and cannot compute is just beautiful at times. I mean, it's just breathtaking. You can actually prove mathematically that some things are impossible to compute. They're just not possible. And when we come to do that, I think you'll be fascinated by it. In fact, I'm toying with the idea. I'm debating with myself at the moment. I may give a few extra lectures. I'll throw them in that are not in the text, but related to Turing and a little bit of the history of how Turing's concept. I'm jumping ahead a bit here. Later, about halfway through the text, Turing's idea of a general programming device, well, strictly speaking, it's a universal Turing machine, but don't worry about what that is yet. And from that came the notion of a programmable computer. So, but what Turing was doing at that time was considering a problem in pure mathematics, like the foundations, philosophical, mathematical foundations of mathematics. He was trying to solve a problem posed by a brilliant German mathematician by the name of Hilbert. So, in a sense, the theory of computation arose historically out of thinking about the foundations of pure mathematics. So I might talk a bit about that and its links with Gödel, the famous Gödel, so pretty well the most famous logician who's ever lived, or, well, debatable. Aristotle would also be out there amongst the top two, but Gödel would be in the top two at least. I may give a few extra lectures on that. So, the link Gödel, Turing, and the historical origins of the notion of a programmable general purpose computer. Another genius, von Neumann, Johnny von Neumann, a Hungarian-American. He was a polymath, obviously a pure mathematician, definitely, a computer pioneer, computer architect. In computer science, you probably heard of the von Neumann architecture. That was obviously from him. So von Neumann was very impressed by Turing. He's older than Turing. In fact, so impressed that von Neumann invited Turing to stay in America and work with him, work together. And that was much the time that von Neumann was so inspired by the basic ideas of Turing, the idea of that would be possible to build a machine that would be, well, two things. General purpose, you could use it to calculate virtually anything, and to have it programmable, right? So von Neumann was inspired by Turing's ideas, and then he proceeded to create an architecture. Well, actually, there's a bit of dispute because he started collaborating with a project that was already existing by two Americans, but he wrote it up. He wrote a report on the design of a programmable general purpose computer, highly inspired by the ideas of Turing, and the world read the report and gave all the credit to this particular kind of architecture to von Neumann, whereas the architecture actually came from the two main guys who sort of brought von Neumann in as a kind of consultant. Or actually von Neumann sort of imposed himself, but he was reputed at the time to be the world's smartest man, and it's a bit hard to reject somebody of that status because, all these stories, well, about Turing as well. Famous people tend to get stories made about them. Von Neumann was so smart, and one of the stories is he could go into a seminar. Halfway through, he missed the first half, and literally in about 5 minutes, he would pick up the general story of what the guy giving the seminar was talking about, and within 5 minutes, he's correcting the errors in thinking of the guy giving the seminar in virtually any topic in math. Right? He was just so brilliant. for example, in I think it was in Vienna, early 30s. So Gödel, the famous logician, mathematical logician, he had very recently discovered his great, famous incompleteness theorem. So he talked about it. There was a conference, a couple of days conference, and I think he was on the third day. So considered, he's very young then, and so he was slotted in for a minor talk, whereas the big players, the big names, they were in the first and second day. And von Neumann was in the audience, and what Gödel had to say was so novel, and its implications so enormous and profound, that virtually everybody else didn't take it in. Like the guy who was writing up the report of that conference did not even mention Gödel. One of the historical oversights, something to his great embarrassment for the rest of his life, I suppose. He did not even mention Gödel's talk. There's this history-making talk. But one person did, besides Gödel, von Neumann. Von Neumann could seize immediately the enormous implications for mathematics, for the foundations of mathematics, of Gödel's famous result, his incompleteness theorems. And he buttonholed, if you're not a native English speaker, he really questioned seriously Gödel about his work and ideas, because von Neumann could readily see the enormous implications of Gödel's work, because it just killed Hilbert's vision of creating a set of axioms, a so-called formal system, which would allow you to prove consistently, without any contradictions, all mathematical statements. So it's a kind of mechanism that would allow you to prove anything, and prove it consistently. So that with those set of axioms, this formal system as it's called, you could not, from